we will continue to study examples of groups. In particular, today we'll look at matrices, which are rectangular arrays of numbers. Now in our class, we'll focus on 2 by 2 matrices. So 2 rows going across and 2 columns going down. Also, for this example, we're going to assume that all entries, meaning numbers, are in Z10. So let's keep that in mind as we do some computations with these matrices. So first, let's see how we can add a pair of matrices together. Now, adding matrices is fairly straightforward. We just add the corresponding entries. So for instance, to add these 2 matrices, we go top left, 1 plus 5. Those go in top left, add them together. Top row, second column, so 2 and 6. Add those together, the top right entries. Bottom left, 3 plus 7. And bottom right, 4 plus 8. So let's add them together to get the final sum. 1 plus 5, 6. 2 plus 6, 8. 3 plus 7 is 10, but we're in Z10, so that becomes 0. And 4 plus 8, 12, mod 10 is 2. So there's our sum, 6802. Now let's see how we can multiply matrices. Now you might think, well, let's just multiply the corresponding entries, but multiplying matrices is a little more complicated. So let's take it step at a time, and we end up using a technique called the dot product, which I'll demonstrate in this particular example. So let's start. Let's say we want, now I should mention our final product is still going to be a 2 by 2 matrix. So let's go one entry at a time. So let's say we want this top left entry. That's the first row, first column. So the yellow entry is first row, first column. So to find that number, we take the first row of our first matrix and the first column of our second matrix. So it's always going to be the row of the first matrix and the column of the second matrix, and then take their dot product. So what do we mean by that? Well, it's 1 times 5 plus 2 times 7. So it'll be 1 plus 5 plus 2 times 7. And that's the yellow entry. Now let's go to the red entry. So that's still first row, but the second column of our product. So now we need to go to our original 2 matrices and look at the first row of our first matrix and the second column of our second matrix. Taking the dot product, that would be 1 times 6 plus 2 times 8. So 1 times 6 plus 2 times 8. Now let's go to the blue. So this is now second row, first column. So we go to our original pair and we go to second row, first column, and taking the dot product, that gives us 3, 5 plus 4, 7. So 3 times 5 plus 4 times 7. And last but not least, now we're talking second row, second column. So let's go to our original 2 matrices. And we have second row, second column, taking the dot product. That would be 3, 6 plus 4, 8. 3, 6 plus 4 times 8. So now let's compute these and reduce them mod 10, which means we only have to focus on the ones digit. So this would be 5 plus 14 or 4, so 5 plus 4 is 9. This would be 6 plus 1's digit only, so 16 is 6. So 6 plus 6 is 12, which is 2 in Z10. Again, focusing on the 1's digit, so 15 becomes 5. 28 becomes 8. 5 plus 8 is 3 in Z10. And this is 18 becomes 8. 32 becomes 2, which is 0, adding those together. And so our product is 9, 2, 3, 0. Now you might be wondering, why is multiplication of matrices have to be this peculiar, a little complicated? Very briefly, the reason is when you study linear algebra, you might learn that matrices are used to represent a special type of functions called linear transformations. And multiplying matrices this way corresponds to composing those linear transformation functions. So that's why we multiply matrices in this manner. I should also point out or reiterate that when you add a pair of 2 by 2 matrices, the sum is still a 2 by 2 matrix. Likewise, when you multiply a pair of 2 by 2 matrices, the product is still a 2 by 2 matrix. So that's something to keep in mind as well. Now, just like we did with permutations in the previous lesson and symmetries the lesson before, we are going to collect all 2 by 2 matrices with entries in Z10 and put them in a set. And that set will be called M of Z10, M for matrices. So for example, we have alpha and beta, which are elements of M of Z10. So that means they're 2 by 2 matrices, entries in Z10. Alpha might look like 1, 2, 3, 4, and beta might look like 5, 6, 7, 8. And so that's M of Z10. Now just a few remarks about this set M of Z10. First, it's closed under addition and closed under multiplication. In other words, when you take a pair of 2 by 2 matrices, add them together, still a 2 by 2 matrix. Likewise for multiplication, and we saw that in the previous slide. Another remark about addition and multiplication in M of Z10 is that both operations are associative, meaning we can move parentheses around. For the explanation of why addition and multiplication in M of Z10 are associative, please take a look at Chapter 7 reading. Now please pause the video and work on Day 7 classwork, and we will go over some of the problems and concepts afterwards. Let's take a look at the following claim, namely, M of Z10 with addition is a group. Now remember that M of Z10 is a set of 2 by 2 matrices with entries in Z10. We'd already seen a couple of the group properties. In particular, M of Z10 is closed under addition. You add a pair of 2 by 2 matrices, still get a 2 by 2 matrix. Also, addition in M of Z10 is associative, meaning we can move parentheses around and regroup. For that, for associativity, please take a look at Chapter 7 reading. Now in the classwork, we saw that the identity property is satisfied, meaning M of Z10 has an additive identity. I'm going to focus additive here because our operation is addition, and the additive identity element is the 0 matrix, 0, 0, 0, 0, and we saw that when you add the 0 matrix to any matrix alpha, we still get alpha, or alpha plus the 0 matrix is still alpha. So adding the 0 matrix keeps any matrix alpha unchanged. This is true for all alpha in M of Z10. So we do have an additive identity element. And every element in M of Z10 has an additive inverse. We saw this in the classwork as well. So for example, what's the additive inverse of 1, 2, 3, 4, meaning which matrix, when you add to 1, 2, 3, 4, do you get the additive identity? Well, we saw that that is 9, 8, 7, and 6. And when we add those two matrices together, we get the additive identity matrix, namely the 0 matrix. So we conclude that M of Z10 with addition is indeed a group satisfying our 4 group properties. Now, what about M of Z10 with multiplication? Well, unfortunately, this is not a group, although it satisfies many of the group properties. Now, we'd already seen that M of Z10 is closed under multiplication. You multiply a pair of 2 by 2 matrices, you still get a 2 by 2 matrix as its product. Multiplication in M of Z10 is associative. We can move parentheses around and regroup when multiplying matrices. In fact, we also have a multiplicative identity element we saw in the classwork, the matrix that we'll call epsilon. That's our matrix 1, 0, 0, 1. That has the property that epsilon times alpha is alpha, and alpha times epsilon is alpha for all alpha in M of Z10. And so multiplying with epsilon leaves any matrix unchanged. It's really like with numbers, multiplying by the number 1. And so M of Z10 does have a multiplicative identity. I'll emphasize the word multiplicative because we are multiplying here. And that multiplicative identity element is the epsilon element 1, 0, 0, 1. So first 3 group properties satisfied, but it's the 4th one, the inverse property, that fails. Now, in order for this to be a group under multiplication, every element would have to have a multiplicative inverse. But we saw in the classwork, for instance, that 2, 3, 0, 0, this matrix can't possibly have a multiplicative inverse because if you multiply this with any matrix A, B, C, D, we saw in the classwork that the bottom row would be 0, 0. So there is no way we would get the bottom row of 0, 1. And so this is impossible. And therefore, for instance, the matrix 2, 3, 0, 0 does not have a multiplicative inverse. And therefore, that property fails, unfortunately. And thus, M of Z10 is not a group with multiplication. Now, let's talk about the notion of a determinant, which is a number that's associated with each 2 by 2 matrix. So here's a definition. We'll let alpha be an element of M of Z10. And let's be more concrete and say that alpha looks like A, B, C, D. So those are the 4 entries of alpha. Then the determinant of alpha, which will denote det alpha for short, is given by AD minus BC. So we take the main diagonal entries A times D and subtract B times C. And note that this determinant is a number in Z10 because we're multiplying and subtracting numbers in Z10. So for example, if our alpha is the matrix 2, 1, 5, 4, then the determinant is the main diagonal 2 times 4 minus the other diagonal 1 times 5. And when we do that, we get 8 minus 5, which is 3. And note that that's a number in Z10. So, well, then what? What do we do with determinants? Well, lots of things, but in particular, determinants can be used to find multiplicative inverse of a matrix, provided that a multiplicative inverse exists. And so let's take a look at our matrix 2, 1, 5, 4. What is its multiplicative inverse, which we'll denote using the notation alpha inverse? Well, it has multiple parts to it. First is that we take the multiplicative inverse of the determinant. Remember, we saw that the determinant was 3 for this matrix. So we take the multiplicative inverse of 3. And then we have this matrix, which is not the original alpha. What we did here, as you saw in the classwork, is we swapped the entries in the main diagonal. So we swapped the 2 and the 4 and made it 4 and 2. And then we negated the other diagonal. So instead of 1 and 5, they become -1, -5. Okay, so we take the multiplicative inverse of the determinant, and then we do the swap and negate. Now let's take this a little further. What is 3 inverse in Z10? Well, 3 inverse in Z10 is 7, because 3 times 7 is equal to 1 in Z10, which means 7 is the multiplicative inverse of 3. And then for 2, let's keep them as they are. -1, -5 in Z10 becomes 9 and 5. Keep in mind, all these numbers that you see are in Z10. And now we can multiply. So 7 times 4 is 28. Mod 10 is 8. 7 times 9, 63. Mod 10 is 3. 7 times 5, mod 10 is 5. 7 times 2, mod 10 is 4. And so here is our inverse matrix 8, 3, 5, 4. We claim is the multiplicative inverse of alpha. And we'll leave it up to you to actually multiply this matrix here, 2, 1, 5, 4, with this matrix here, 8, 3, 5, 4, and show that their product is epsilon, meaning 1, 0, 0, 1. And if you go alpha inverse times alpha, so this matrix times this matrix, again, I'll leave it up to you to verify that that also equals epsilon, namely the multiplicative identity matrix 1, 0, 0, 1. So do keep in mind that epsilon here is 1, 0, 0, 1. So we'll leave that calculation up to you. But that's the end of this lesson. So I will see you next time.